This is a short video on the Laplace transform, its mathematical definition, how you can determine the Laplace transformation of a given function, and some properties of this transform. So for a given function f of t, for which ft equals 0 for t smaller than 0, we can define the Laplace transform f of s. This is typical notation, is L of ft is the integral from 0 to infinity of ft times e to the power of minus st dt. So it's an integral over time, but we introduce the variable s, and that is a complex variable. If we perform this integration, we'll have the Laplace transform of f. Now we can do this for a lot of functions f, but as f will be can be the input for a system. Before we saw a little control system with an input and an output, that ft can be an input. I will show you three basic ones, and one is an impulse, which is an infinitely high but infinitely narrow pulse, which is called a Dirac pulse. Another one is a step function. So imagine turning a system on and applying a certain force or current or voltage. This is where we go from 0 to a step, and I will take the height here to be a step of height a, but we could also do unit step or a step of 2. So our function basically goes like this. And we can have a ramp where we slowly increase the input of a system. Now this one I will leave to the theory. This one, where we have ft is equal to a, and here ft is equal to a times t, we can take the Laplace transform of. So I will do it for this one, which I guess is the easiest one. If we take the Laplace transform of ft is 0 to infinity a times e to the power of minus st dt. Well, we could take the a in front of the integral, and we can take the integral of e to the power of minus st, and we are left with minus a over s e to the power of minus st between the limits 0 and infinity. Now if we want to do this neatly, we would take the limit here, but as we know that e to the power of minus st goes to 0 as t goes to infinity, we are left with 0 minus whatever we get when we enter in 0. E to the power of 0 is 1, so we get plus a over s. And this is our Laplace transform. So we've done this now for one of the most simple functions. If you wanted to know what the Laplace transform was of this one, it is simply, if the pulse has a surface area of a, it is simply a. Now if we want to do this one, we need 0 to infinity. Let me just slow that down. We want the Laplace transform of our ramp. So we want the Laplace transform of this f of t, which is 0 to infinity at e to the power of minus st dt. Now this one we can't integrate in one step. We'll have to use integration by parts. And for that, I will take one function, this one, which I will, in my notation, call large g, because that's the one I want to differentiate. And here I have a small h, and that's the one I'm going to take the primitive function of, which is then my big G, at, times the primitive function of that, which is minus 1 over s e to the power of minus st between the limits 0 and infinity. And from that I have to subtract the derivative of this one, which is simply t, times the primitive of that one, minus 1 over s e to the power st dt, between the limits 0 and infinity. Now, if I look at this one, I know that if I let t go to infinity, the exponential function decays to 0. So this bit is 0 minus whatever I get when I put in 0. Well, the exponential will become 1, but if I put t is 0 in here, I end up with 0. So this whole integral is equal to 0. Now let's look at this one. This is an integral in t, so that I can take a and minus 1 over s and move it in front of the integral. I cancel this minus sign and I am left with a over s integral from 0 to infinity e to the power of minus st dt. And now this is one we already solved over here, and we are left with a over s times 1 over s, which is a over s squared. So for 3 of the most basic functions, we now have the Laplace transform. Well, will it be necessary for us to calculate these integrals? Well, for simple ones, yes, you can do that by hand, but if it becomes more complicated, there is no need to, because every textbook we have, including the one we use for this course, will have a Laplace transform table for the forward Laplace transform, where we take a function and desire its Laplace transform, so this way, but also for the inverse Laplace transform. So it is not necessary to calculate all these integrals by hand every time. We can simply use our table. But there are some properties of the Laplace transform which are very important. One, it is a linear transform. It is linear. And that means the following. If I take the Laplace transform of a constant times a function, well, we can use the definition of the integral. That is 0 to infinity k times f e to the power of minus st dt. I can bring that constant forward in front of the integral, which is k to the times the integral 0 to infinity ft e to the power of minus st dt, and that is k times the Laplace transform of ft. So if I have the Laplace transform of a constant times a function, that is the same as having that constant times the Laplace transform of that function. That is the first one. And the second one is that if I take the Laplace transform of a function f plus a function g of t, I can write that out as the integral again, ft plus gt times e to the power of minus st dt. And using the rules we have for integration, we can separate this out into two integrals. The one for f, e to the power of minus st dt, plus the integral for g, e to the power of minus st dt. And we see that this is simply the Laplace transform of f, and we add to that the Laplace transform of g. So I have that if I take the Laplace transform of a sum, it is equal to the sum of the two Laplace transforms. So, using this property, some of the simple functions and our lookup table, it becomes a lot easier to work with the Laplace transform. I will give you the first part of that table, which we will use later in an example on differential equations. So if this is my f, then this is the Laplace transform. So we had a unit pulse and we ended up with 1. If we have a unit step, which is denoted by a 1 times t, then our Laplace transform, well, in the example we had a step with height a, but this will then be 1 over s. If we have a ramp t, then we'll get 1 over s squared, and there are a couple. If we have t to the power of n minus 1 divided by n minus 1 factorial, this makes it easier to go back and forth. As I shall show you, this will be 1 over s to the power of n, and t to the power of n, which you were expecting, is then n factorial over s to the power of n plus 1. The exponentials are really important here. E to the power of minus at. The transform is 1 over s plus a, and t e to the power of minus at is equal to, well, the Laplace transform is 1 over s plus a squared. So we now have our basis. We have some functions where we know the Laplace transform, we know some properties, linearity properties, or they're also called the principle of superposition, which is exactly the same. A term used more by physicists than mathematicians. And I will just leave that out there. All right, so we don't always just look at the function. Sometimes we take a function that we know and we change it. So if we take a function, just any function, f of t, sometimes we want to shift that function over a distance alpha. And to write out the mathematical formula of this function given f of t, well, we can also write this one as f times a unit step function, so that we ignore everything that is to the left of the origin. And then this will be f times t minus alpha times the unit step of t minus alpha. So this is basically a shift to the right. Now, if we take the Laplace transform of f t minus alpha times that unit step, so the function shifted with amount alpha, what we get is e to the power of minus alpha s, times f of s. And if we multiply it with an exponential of e to the power of minus alpha t times our function, we end up with f s plus alpha. So it's a shift in time domain, so a shift here, and a shift in Laplace, well, in s domain, yields an exponential in front of our f, or f multiplied by an exponential. So these are shifts, but one operation we see a lot more of in differential equations is the derivative. So if, let's say we have some f of t, and we take the Laplace transform of df dt. Then we end up with s times the Laplace transform of f minus f at t is 0. So this is the initial condition. If we look at the second derivative, d squared f dt squared, then that's equal to s squared fs minus s times f0 minus f dot 0. And the dot notation means that well, is equivalent to the derivative in time. So this is the value of the first derivative of f at t is 0, and these values we take from our initial functions f. So these are the initial conditions in for the function itself and the time derivative. So let's see what would happen if we take a differential equation. Yep. So if we have m x double dot, so the second derivative of x plus b times the first derivative plus k times x equals some input. These are the basic form of a mass spring damper system with some form of input. Now, I want to relate this first back to the video we had on why the Laplace transform is here. And using this, what I'll do, I'll start with the initial conditions. x0 is the same as its first derivative, so they are both 0, so the system is in rest, and then we apply some form of input. So if we look at the Laplace transform of this equation, we know that the second derivative yields s squared times the Laplace transform of, in this case, our x, but all our initial conditions are 0. So here we have m times s squared times the Laplace transform of x plus b times s times the Laplace transform of x here, because our initial condition is 0, plus k times the Laplace transform is equal to u of s. Now here we have three terms with the Laplace transform of x in each of the terms, so we can write this as m s squared plus bs plus k times x of s is equal to u of s. And if we now want to find the transfer function is the fraction of the Laplace transform of the output over that of the input, and we get our transfer function like this. And if we now wanted to look at the stability properties, we could. So here, this is how we find the Laplace transform of our, I guess, our system. But we can do a lot more with that, because one of the things we wanted the Laplace transform was so that we can solve differential equations. And I'll have an example now of how we can solve two differential equations that we may have seen in engineering mathematics and modeling using this table and some basic mathematics with polynomials. And first, let me get rid of this. So we'll have a differential equation, y double prime plus 5y prime plus 6y equals 0, where we have that y at point 0 is equal to 0, and equal to 1, and the first derivative at t is 0 is equal to 0. We will take the Laplace transform of this differential equation, and we end up with, well, the second derivative was equal to s squared times the Laplace transform of y minus s times the initial condition at t is 0 of y, so that is 1, minus the initial condition of the derivative, which in this case is 0. Then the Laplace transform of 5 times y prime, which is 5 times y, 5 times s times y of s, minus 5 times y0, which is 1, plus 6 times the Laplace transform of ys, and that is equal to 0. Now, I've used both rules for linearity here because this is a sum of different functions, and so I've taken the Laplace transform of the first plus the one of the second plus the one of the third. So this is where I use the Laplace transform of a sum is equal to the sum of Laplace transforms. But also here I have a factor 5 and a factor 6, and you see that they that the Laplace transform of a constant times a function is equal to that constant times the Laplace transform of that function. So I've used both rules implicitly. Well, explicitly. So we can take all the terms with ys together, and we end up with s squared plus 5s plus 6 times the Laplace transform of s. And we still have, let's see, we have minus s here, we have a plus a minus 5 here, and so we have minus s minus 5, and that is equal to 0. We'll move this over to the other side, so we end up with s squared plus 5s plus 6 times y of s is equal to s plus 5, and then we will divide left and right by this polynomial, and we find that the Laplace transform is equal to s plus 5 divided by s squared plus 5s plus 6. Now, nothing revolutionary here. We just know that we have the Laplace transform. But we don't have it in any of these forms yet. What we'll need is something called partial fraction expansion. And that is something which I'll leave to a next video. But it means that I can write, because I know that s squared plus 5s plus 6 can be written as s plus 2 times s plus 3. I can write this as a multiplication of two terms. I can write this as some fraction over s plus 2 plus some fraction over s plus 3, and I still have to figure out what a and b are. Again, I will leave that for a separate video. This is minus 1, and this is equal to 2. So these fractions, these partial fractions, now we know that, well, now they look like something that resemble something here, namely something like something in the form 1 over s plus a, which we know if we do the inverse Laplace transform, we know that it ends up being an exponential. So we can write this as minus 1 times 1 over s plus 2 plus 2 times 1 over s plus 3. And these functions, I can take this table and look at what the original function should be. And again, the Laplace transform is linear, but it's the inverse Laplace transform is also linear. So this is, if I now want y of t, which is the inverse Laplace transform of y of s, is the inverse Laplace transform of -1 times 1 over s plus 2 plus 2 times 1 over s plus 3. Now I again use the principles of linearity, which is equal to -1, the inverse Laplace transform of 1 over s plus 2, but I know this one because that's in my table, plus 2 times the inverse Laplace transform of 1 over s plus 3. And again, I know these, and what I get is -1 times e to the power of -2t plus 2 times e to the power of -3t. And there are two interesting things that we can deduce from this, is that we don't have any constants. The initial conditions that we set are already incorporated in our answer. This is the solution to the differential equation. Where normally we would take the characteristic equation and then find the homogeneous solution. Now this is a homogeneous equation, so it doesn't look like we're saving time here. But once we start making this more complicated, this system, this method of the Laplace transform will be infinitely easier, but it will be also a lot easier to look at the Laplace transform here, or the Laplace transform of a system, and look at its behavior. We don't have to go all the way back to a function of time. But we started with our differential equation, took the Laplace transform, were able to find an expression for the Laplace transform of y. Using partial fraction expansion, which I will cover in a future video, we're able to write this out in a form that is in our lookup table, and we were able to find the particular solution of this differential equation. I will do another example where, well, here this was a homogeneous equation. Now we will add some form of input. And just for this example, I will set both initial conditions to 0, and I will have as an inhomogeneous component 2. So again, we can take the Laplace transform, and now I have a constant function, so I'll end up with a 1 over s. S squared times the Laplace transform of y, well, minus s times the y0 minus y prime 0, but these are both 0, so I'll leave them out, plus 5s y of s plus 6y of s is equal to 2 over s. Again, we take these terms and group everything with the y of s, which on the left hand side is everything. S squared plus 5s plus 6 times y of s is equal to 2 over s, and we can write our Laplace transform of y as 2 over s times s squared plus 5s plus 6. Again, using partial fraction expansion, and we can write this as some fraction over s plus some b over s plus 2 plus some c over s plus 3. And we can calculate a, b, and c. And in our case, this is equal to minus 1, 1/3 times 1 over s plus 2/3 times 1 over s plus 2. That's the s plus 3 term, minus 1 times 1 over s plus 2. So now I have these coefficients here. And we have fractions 1 over s, 1 over s plus 3, and then 1 over s plus 2, which I can find over here. And remember, 1 over s is just simply the unit step, so that will end up being a constant. So my overall solution to my differential equation is 1/3 plus 2/3 e to the power of -3 minus 1 e to the power of -2. And this is my solution to my differential equation. And so I hope you can see that this is a very powerful way of solving linear differential equations. Finding this partial fraction expansion is very easy to do with the computer and relatively easy to do by hand as well. This just allows us to solve differential equations in a different way, but then also use it later on in control theory, where trying to solve it in the way we learned in engineering mathematics and modeling would just simply not be very convenient. All right, so this was an introduction to the Laplace transform.